had started looking at the behavior of specific heat of the electron gas and trying to understand from where from does the specific heat of the electron gas arise and what is its value. If you consider the electron gas as was considered by Drude within the purview of kinetic theory of gases, then you will get a number like 3/2 R. However, what was seen, as I have already discussed, was that the specific heat of the solid which has the atomic lattice, the ionic lattice, which is the arrangement of these ions, and it also has the electron gas inside it. So, the net specific heat is the specific heat of the ions inside the solid as well as the electrons, and if you measure the specific heat of the solid, it is nowhere close to 3/2 R, but it is actually 3 R. As you reduce the temperature, the specific heat goes down as T cube, and then at very low temperatures you have a linear temperature dependence of the specific heat. This entire regime of temperature where you see the T cube dependence and the 3 R dependence, this is all coming from the vibration of these ions inside the lattice. However, you get this linear temperature dependence at very low temperatures, which are sub Kelvins, often sub Kelvin temperatures, very low temperatures below 4 Kelvin. In these very low temperature regime, you start seeing, rather than this T cube dependence, you see a linear dependence. Okay? And this linear dependence arises because you have actually frozen out the vibrations of the ions. So, you no longer have this term which is coming from the specific heat of the behavior of the ions, from the vibration of the ions, is no longer present. What you have only present is the electrons, and these electrons now start contributing to the specific heat. So, if you change the temperature at these low temperatures, slight variation in temperature actually changes the energy of this electron gas, and that gives rise to the specific heat. And what was seen was that it has a linear temperature dependence, and this specific heat of the electron gas is almost 0.01 of 3/2 R. This is the value which you get from kinetic theory of gases or within the Drude's model, but the actual specific heat of the electron gas is far lower. This value of the specific heat is far lower than 3/2 R. It is typically 0.01 of R. So, where from is the specific heat of the electron gas coming? And this is where Sommerfield's idea became very successful in explaining this linear temperature dependence of the specific heat and why is it so much lower than 3/2 R. And where from does the specific heat arise? Within the Sommerfield's model, you have these different energy states which you have from the periodic boundary conditions. You have different energy states. You start filling up these states at low temperatures up to the Fermi level, the states are all filled up. And at this low temperature, if you change the temperature slightly, say you increase the temperature slightly by dt, then the electrons which are present within kB dt of this Fermi energy, the electrons which are present within a small region of the Fermi energy which is of the order of kBt, those electrons will absorb the thermal energy and will get excited to higher energy states. And as a result, the electrons which were initially occupying only up to this energy level will now start occupying higher energy levels, and so therefore their dE will also go up. So, as you increase the temperature at the low temperature, because of these excitations of the order of kBt around the Fermi energy, the average energy of the system also rises, and intuitively you can guess that as you increase the temperature you can acquire higher and higher energy states, there will be more change in the average energy of the system, and so the specific heat should start increasing as a function of temperature. And this was a very successful contribution and the basic idea of calculating the specific heat of the electron gas inside a solid. So, let us go about calculating this specific heat. Now that the picture is in mind, let us calculate the specific heat of the solid, and the first thing to do is that we would like to know how much is the change in energy of the system which is defined as the total energy of the system, the total energy of the electron gas at temperature T minus the total energy of the electron gas at 0 Kelvin. Now, if you recall, we had introduced the concept of the density of states, and G of Ek Fermi Dirac Ek minus mu was the occupancy of states at Ek. This is the density of states at Ek, and this is the probability of occupying those states. So, what is the density of occupied states? You may also call this as the density of occupied states is nothing else but this quantity, density of occupied state. So, the number of occupied states between energy range Ek and Ek plus dEk will be G Ek F d Ek minus mu dEk. This is the total number of states between Ek and Ek plus dEk which are occupied. Each of these states has energy Ek. So, the total energy of the system between Ek and Ek plus dEk occupied states is equal to Ek G Ek F d Ek minus mu dEk. This is the number of occupied states between Ek and Ek plus dEk, and this is the energy of each of the states. So, this gives you the total energy of which is present between Ek and Ek plus dEk, okay. And so, the total energy of the system is nothing else but, if I integrate from 0 to infinity, all the energy states which are available from 0 to infinity, Ek G Ek F d Ek minus mu dEk. This gives me the expression for the total energy of the system. For this Sommerfeld system, where the electron is a quantum particle, and this is the total energy at a given temperature T. And what is the energy at 0 temperature? The energy at 0 temperature is nothing else but 0 to infinity Ek G Ek F d Ek minus mu at 0 temperature dEk. But what is the Fermi Dirac distribution? Ek minus the chemical potential at 0 temperature. The chemical potential at 0 temperature is nothing else but the Fermi energy, which we have already calculated. This is Ek minus Ef. The Fermi Dirac distribution Ek minus Ef, which at 0 temperature is 1 for all energies which are less than or equal to Ef, and it is equal to 0 for all energies greater than Ef. So, this range of energies which is going from 0 to infinity, this will pick up a 1 only from 0 to EF, and for all energies above EF this factor will become equal to 0. So, therefore, the energy at 0 temperature will be integral 0 to EF Ek G Ek Fd Ek minus EF dEk plus integral EF to infinity Ek G Ek Fd Ek minus EF dEk. This is 1, this is 0. In this range from energies which are above EF, the Fermi-Dirac distribution is 0. So, this becomes equal to 0 to EF Ek G Ek dEk. So, therefore, if I write how much is the change in energy, which is equal to the total energy at a given temperature minus the energy at 0 temperature, this can be written as 0 to infinity Ek G Ek Fd Ek minus mu dEk minus integral 0 to EF Ek G Ek dEk. Now, this integral we start, now this is the chemical potential at a finite temperature T, which is not equal to 0. This is T is not equal to 0. Now, this integration I change it from 0 to EF Ek G Ek Fd Ek minus mu dEk plus integral EF to infinity Ek G of Ek Fd Ek minus mu dEk minus integral 0 to EF Ek G Ek dEk. Let us call this equation as equation 1, okay, where I have just rewritten this by taking it from 0 to EF and EF to infinity, and then let us look at what are the contributions, because you know that at finite temperature the distribution becomes, it is no longer like this, but the distribution. So, there are electrons from below the Fermi energy have got excited to states which are available above the Fermi energy. This is the Fermi-Dirac distribution, this is 1, this is the energy. So, for electrons which are roughly below the chemical potential, those states have got unoccupied and electrons have got excited. So, we are breaking it up into two parts, one is up to EF and the other is from EF to infinity. Let us look at another term, the total number of electrons. The total number of electrons can be written as 0 to infinity G of Ek Fd Ek minus mu, which is a function of temperature dEk, this is at finite temperature, which is also equal to integral of, this is n by V, the density, okay, which is equal to 0 to infinity G Ek Fd Ek minus mu at temperature T equal to 0 dEk. This is the definition of the total number of electrons. If you recall, the total number of electrons was twice summation of k Fd Ek minus mu, okay. This is the definition at any temperature, which can be written as, for 0 temperature Fd Ek minus mu at 0 Kelvin, which is twice of summation over k Fd Ek minus Ef, because mu at 0 temperature is this at 0 temperature is at EF, and this is at finite temperature, this is T not equal to 0. So, this expression can be rewritten like this: density of states at Ek, the density of states into this, and 0 to infinity. This we can break it up into two limits. So, we can rewrite this as 0 to EF G Ek f d Ek minus mu d Ek plus integral EF to infinity G Ek f d Ek minus mu d Ek is equal to integral 0 to EF G Ek d Ek, because f d Ek minus EF is equal to 1 for Ek less than or equal to EF and is equal to 0 for Ek greater than EF. So, if you put that here in this expression, anything which is greater than EF will pick up a 0. So, you will not have the, and whatever is below 0 is into 1. So, this, and now this expression, this entire expression, you multiply it by EF. So, you will get integral 0 to EF into G Ek f d Ek minus mu d Ek plus integral EF to infinity Ek G Ek f d Ek minus mu d Ek is integral 0 to EF Ek G Ek d Ek. So, I can write my integral EF to infinity Ek G, so not Ek, this is EF, this should be EF, this is EF. So, this integral EF G Ek f d Ek minus mu d Ek is equal to integral 0 to EF Ek G Ek d Ek minus integral 0 to EF EF G Ek f d Ek minus mu d Ek, and this is my expression 2, and I take expression 1 minus expression 2, where expression 1 is the earlier expression, this expression. From this expression I subtract this. So, with that we can get a term for this.